all. This is Darryl Jr. Back as scheduled this weekend to talk about a few interesting subjects. Uh, Somebody asked in the comments about detecting the motion of the Earth, and someone else asked about pear-shaped Earth or an Earth from far away. So basically, the motion of the Earth and the shape of the Earth. So I plan to share one of the Himurari 8 satellite photos, but it seems like the site is down right now. It's not working at the moment. But there's other things I can show as well until that site kind of comes back up. And so, and as you join, go ahead and make sure you drop a comment in the live chat. Let me know you're here, like and subscribe if you haven't already. And we'll go ahead and make this thing work. Now, starting with detecting the motion of the Earth. Um, I know there's one. Hey, what's going on, Lisa? Good to see you. And you are showing up as Lisa, by the way. So I'm not sure why sometimes you comment it shows up as the other name. What's going on, Catherine? Awesome. Welcome. Glad you're here to hear about these interesting topics. And yeah, interesting. But one thing I do notice when I stream, apparently there's another sign in, some kind of ghost sign in or something, and it I notice sometimes I'm still under my other account. I don't know, it's weird. But what I started to do is just not signing into that one and just typing here, and it always keeps the name of the channel I'm streaming on. So I don't know what's up with that though, but it may be something to do with the signing thing that's going on. But awesome. For detecting the motion of the Earth. First thing that comes to mind with that, so you all probably heard it before, something called the Foucault pendulum. Um, and basically what they did was you would take a long enough pendulum and set it upon the Earth. And usually these things have some kind of motor. So, it's an extremely long pendulum. Maybe it has a little bob on the end. And I've actually seen people do this experiment. And if you make it extremely long so that an extreme amount of mass, so it's not easily swayed by air or something like that, is long enough so that the slow spin of the Earth can be detected. What happens is if you let this thing spin, and let's say you put a marker on it, so as it spins, it marks the ground. And what'll happen is if you let it continue to spin, it'll start to rotate, and the amount of the rotation, the angle, will determine your latitude on the Earth. That's pretty cool. That's one way that people have determined the rotation of the Earth. Another thing, ironically, is something that was done by a flat earther. Maybe I should pull that up. I believe his name was Bob Nodell. Now, I never understand why people do that, why they spend so much money on these there's this thing going on, they're calling it the Flatlined experiment, where apparently they want to pay for flat earthers to go to Antarctica or something. It's like, why wouldn't you spend that money on people who yeah, exactly. The flat earthers have some of the best evidence for the globe. But why wouldn't they spend that money on, I don't know, somebody who's making an undergraduate student that's doing incredible research, send them there, and maybe they want to extend their. I don't see any reason to spend all that money on dishonest people and stupid people. But that's what they do for some reason. I don't know why. But the Veritas documentary, ironically, about flat earthers, they actually showed that. And basically, Bob Nodell apparently took one of these advanced gyroscopes that shaped something like this, and what's that drawing? Shaped something like this, and it was very high tech, has dials on it and everything. And he used this thing to detect the motion of the Earth and he detected a 15-degree per hour shift. So the way that works is if you have 24 hours and you multiply that by 15 degrees, you end up getting 360, which, the Earth is a globe. So if you multiply that, so it on the calculator, wait for 24 times 15, 360, which relates to the, circle, the globe of the Earth. The circle being if you just take the XY plane that is rotating on. So that's two simple ways that we can understand that the Earth is moving and in motion. So it doesn't take much from the rotation. So I believe it was last week I talked about the protoplanetary disk and how we understand that the initial motion of the solar system and the planets and everything comes from the original motion from the large gas cloud that formed this planet. One of the things we actually covered in my my astronomy research class is the technology that we have now. They can look very, very far into the past, which is far into the universe, and they found what they believe may be one of the earliest star-forming regions. They called it the Grape Cluster because the way it's shaped is shaped something like, at our resolution, we can't see it in much detail, but they determined sort of 15 clumps of star-forming regions. I don't know if that's 15, but I just drew it to look like grapes. And you're familiar with, if you ever had bought some grapes from the store where they all on the vine, it looks sort of like a sort of this shape with a whole bunch of orbs. Or this area of star-forming region looks like that. And the interesting thing is those stars, when they died, so there's helium fusion going on in the center of the star, and basically the helium is fusing into hydrogen, and the energy that's released fuels the sun. And when stars are large enough, the pressure is great enough that it starts to fuse heavy elements, and those heavy elements explode when out of a star when a star goes supernova. When a star is above a certain amount of mass, it goes supernova when it dies, and that mass explodes out and becomes a planetary nebula, they call it. So if you look at the image that I have right now, as a matter of fact, that's an image from the Hubble telescope of the uh, uh, Eagle Nebula, called M16. I calculated as a part of my homework how far away it is. Let me actually pull that up. I may be wrong about the actual number because I'm doing it for homework, but pretty sure I'm right how I did it. I gotta actually show y'all real fast what that was like. Uh, I guess I didn't save my distance calculation. Hey, when it does that, this thing it doesn't save properly sometimes. Like when it's trying to save data, I'm just scrolling to the wrong part. As far as I can tell, it did not save my calculation, so I'm going to have to uh, calculate that part again. And actually, let me go to my actual submission. I could have swore I saw that there. I'm not. Oh, that's what it is. I'm looking at the wrong file. Ah, here we go. All right, so let me share this really fast. So this is the math behind finding that. So the nebula, like the interesting thing about astronomical data is, and you look at that picture right there, the satellites, that's from the Hubble actually, um, and we're going over that in my research class. The devices are so sophisticated that it doesn't take only one dimension of data. Like at this point, they can take data such that every pixel of the photo, not only does it have the color of the photo, but it also has the spectrum. So you could imagine, if I was to draw it out, if you have a pixel, one pixel in the rotation, it has a number of counts. So the number of counts is how bright the thing is. Oh, let me show this again. So each pixel has the number of counts of brightness, but also each pixel is broken up into its component wavelengths. If you saw my debate, you saw some spectra I took of the sun. Well, imagine each pixel has its own spectra just like that, and it can see the wavelengths of light in every pixel. So, and hold on, let me look at the question. Lisa says, is there a minimum amount of mass a star needs to go supernova? Yes, there is. I could find that for you. Yes, thank you, Catherine. And I'll finish going through that calculation. But it'd be good to look up the mass. So I know that, like, when we calculate solar masses, the general ranges of solar masses is going to be about 0.8, 0.8 solar masses, zero point 0.8 or 0.08, one of the two, all the way up to about 100 solar masses. And that's pretty much the range of stars that we find. So what I'll do, I'll pull up my favorite astronomy textbook, my Astronomy Today, and we'll see what the mass is for a supernova. And I'll share that page when I find it. Interesting thing is, we go through all of this stuff, but I can't say I remember all the numbers, but I remember the concepts. But I suppose after a while of going through these things many times, I'll start to probably remember the masses as well. Supernova remnant. Now let me actually share my search here. So what I'm doing, this is my textbook Astronomy Today. And actually it's still an intro astronomy textbook, but it's pretty advanced. There's a lot of good stuff up here. So um, maybe I'll search under stellar masses. They have a whole section in here on stars and stellar evolution. Stellar explosions, that seems pretty good. So now here's an example, by the way, of when a star gets really big. The larger stars, what happens is when they start to die, let me bring my my pad to the front again. So when a star starts to die, when it's very, very large, what happens is it starts to burn up all its fuel in the center. And there's a balance that's going on between the gravity of the star's mass and the pressure of the radiation. And when that's equal, the star has a set size. So what happens is when the fuel starts to run out, the pressure goes down, and that means gravity starts to win. So the star shrinks. But when the star shrinks, the pressure increases and things start to shrink and get closer together. That warms it up as well. So then when the pressure increases, the fusion starts to increase again, because basically fusion, you can say, is a result of pressure sort of forcing um, atoms together because of all the pressure. So then the fusion starts to heat up again in the center of the star. It gets warmer, the pressure increases, and then next thing you know, we have a star that is back to its original size. And if we look at the textbook again, this is what this is talking about. At least a process. So it's saying, if you look at this, it's saying time in days luminosity, right? And you can see this lump right there. I don't know if you can see my mouse, let me know. And when you look at the star, you can see how it goes from dim to bright. That's one of the things that happen with stars when it starts to get really big. But there may be other things that do that as well, but that's definitely one of the things that happens with very large stars. So let's see if we can, oh, here we go. So the end of high mass stars. Collapse of the iron core, supernova explosion. So it looks like I'm surprised they didn't give a mass yet unless I missed it. If y'all see it before me, let me know. These are by the way what supernovas look like during the explosion. Let me zoom in on this. This is a supernova called SN 1987. Ironically, in the astronomical records, we can look in the records and see supernovas from many, many years ago, because people might not have known what it was, but they pretty much describe it as a new star forming in a certain part of the sky. But now we can look at that same spot in the sky with our telescopes and see planetary novas from the explosion. Okay, well, I'll keep that in mind that the point is not visible. But let's see one more time if I can find the mass. It must be up in here. Stellar evolution. Maybe I'll look in the stellar evolution part. Leaving life and death of a star. So sun-like star, red giant branch. So now we're talking about the giants. Those are the ones that usually go supernova. Okay, here we go. This is perfect. This, I believe, has everything that we need. Central density radius. So it has it in terms of radius, but if we wanted to, we can calculate the mass. It's probably going to be in this page here. So what do we have? We have now the thing is, with a star, the bigger a star is, the faster they burn because the pressure is pulling it down. So ironically, if you look at, there's something called an HR diagram. HR, and I can pull that up if y'all like as well. And what they do is they will, let's say, get a cluster of stars and they will investigate every single star. And we know that the temperature of a star is related to its color. What's going on, real kindness? So if a star is blue, it's going to be really, really hot. And if a star is red, it's going to be really, really cool. So what happens is usually the blue stars are up here and the red stars are down here. And the sun is in the middle. The sun is pretty yellow. And this is pretty much the main sequence. And up here, we have some very, very bright stars. These are the red giants. They're cool, but they're very big, so they're brighter. And down here, we have the white dwarfs, which I guess maybe this is a good color to put there. They're very small, but they're very hot because they're pretty much the cores of dead stars. But at the same time, they're very dim because they're so small. So, and the thing is, the lifetimes of these stars, I probably should make these over here a bit smaller. The lifetimes of these stars that are very small, actually very long because they burn so slowly. As a matter of fact, that's one of the hangups that we have about the cosmology is some of these small stars, the universe has not been alive long enough for them to die, so we can't even really age them because we age stars by looking at this diagram. And what happens is there was a line that I saw up in there that talked about the peeling off the main sequence. So if a star is on a main sequence, it's still mostly burning hydrogen. When I talked earlier about a star that was starting to get bigger and smaller, that's when it's peeling off the main sequence. So if we look at a cluster of stars and there's a whole bunch of stars over here, we know that it's a very old solar constellation or cluster of stars. If there's no stars here, but most of the stars on the main sequence, we know it's a very young constellation. But suffice it to say, we can look at the point where the stars start to veer off, and we can age this star, and then we can sort of get the age of the entire thing. Because since this star is about to die, this star is the life of the cluster. So when we get the age of this star from the cluster, then we get the age of the entire cluster. And that's how we can sort of determine how old stellar cluster is. That's sort of an aside background to understand this diagram. So as you can see, it's talking about the next stage of a star, how many years into the next stage. It's talking about the central temperature. And you notice how the bigger the density gets, the hotter the temperature is. And you could see that. You may not be able to see my mouse, but I'll just click this. You can see the density right here. And as you can see, the radius gets bigger as the central temperature gets bigger because the pressure is bigger. So if we're looking at this, something with this density because of this size is a main sequence, subgiant, so on and so forth. So I still have to find out the radius of and here's the HR diagram here, right here. This is what I was talking about. So, you couldn't even see my drawing there. I'm sorry about that. This is what I was drawing though. So if you look at this, in this image here, you can see it. That's exactly what I was drawing. So the main sequence is in the middle right there. where it says main sequence. So this is the main sequence. The red giants are up here, and these ones at the bottom here are very cool small stars. And these up here are very hot on the left. And at the bottom, it relates to the surface temperature of the star. So going back to the book, that's what I was drawing right there. Sorry, y'all couldn't see it at the time, but that's what it was. But in pretty much every astronomy class that you take, you have to, like, the main sequence is very important in determining what types of stars you're dealing with. And there was a bunch of women that they call computers that figured that out. They would actually study the stars, and they eventually started a classification that's still being used today. Even though now we have the technology that can see much smaller stars, so we've increased this. Like, the original classification is this, but now we have Y stars and T stars and believe L stars that are even farther to the right. They're like brown dwarfs because they're so cool that we don't even consider them red anymore. We can barely see them at all. But I'll have to look into that another time and see exactly what the size is. Oh, move closer. Yes, yes. You talking about the table? Yes, yes. I can zoom in closer on that table. And make sure the page is going to scroll. There we go. So here it is. So here's the table with the values in it. And I think that might be visible. And this is again in the textbook Astronomy Today, intro astronomy textbook. I still can't say I'm up to par with all of my more advanced textbook. I mean, I read them through the class, but it was just a whole bunch of complicated stuff that you have to get through. But I'm still inching my way through this one. And let me see if I can get a more advanced HR diagram. What would be good is to show a like a very built up HR diagram. In my galaxies and cosmology class, they showed a like a HR diagram with real stars. Like, it wasn't like an illustration. It was like real stars. And it looked so awesome. Like, whoever got the data from the cluster, they literally took the stars that they got pictures of and at least the data from them and put them all in the HR diagram. This is an example of a cluster, by the way, that they get the HR diagram from. This is what I was talking about, how when they peel off. Let me zoom in on this one. So for instance, they might take this cluster of stars right here. They study each star. And I was mentioning earlier how the technology is so advanced that you can also get the spectra of the star, which will give you the temperature. If you remember that spectra I took of the sun, the peak of it was at about the 500 wavelength, which is consistent with a star with a temperature of about 5,000 Kelvin in the surface. And that's why if you look at this, about 6,000 Kelvin, the main sequence right here, you can see that box. So the sun would be right up in here. As you can see, that's around 6,000 Kelvin. So that's why I've used to go back to the debate I did with Whitsitt. If you look at my spectrum, and if you look at the bottom line where the wavelength is there, this is why so many of my lines are in this area, because that's the peak of where the sun is, with temperature-wise. So, yeah, this is pretty cool. But this is how we get the age of actual clusters by looking at this. Here's another cluster. Look at the stars, and this must be an older cluster because we look at this, a lot of the stars have peeled off the main sequence, which means all of these stars are giants over here. Now, of course, the size is not to scale. Different of these HR diagrams, they might, some of them make it to scale because they're trying to focus on the size of the star. This one is clearly focusing on the age of the cluster. If you want to know about how many stars are in the so basically this cluster has almost no new stars. Basically, the newer stars will be up here, but because they burn so hot, they die more quickly. So that's why what happens is, if you look at an HR diagram, the very young solar system will have stars along this whole diagonal, and the older the cluster gets, the more the peeling ends up peeling off this way, and it's like a banana peeling to the side right here. Stars just dying off the main sequence, turning into red giants. And then next thing you know, this area turns into this big nebulous cloud. Like if I was to go back to my image from the Hubble telescope, so basically many millennia ago, that would have been a whole bunch of stars that all died off, peeled off, just like you saw in the HR diagram, and now it's a nebula. And if you look at these points, these are all star forming regions. And part of one of my homeworks, we had to zoom in on this. So, for instance, this area, the little pink areas, are big star forming regions. And basically, what's going to happen is all the different areas of this are going to form new stars with the new elements that were made in the fusion from the previous stars. I don't know how we got in this tangent, probably because I'm just so interested in this stuff. I think we're, I think we're originally talking about uh, the mass of a star that goes supernova. I still haven't found that yet. But what I may have to do is just make another stream, like let's say the week after next, and maybe talk about the actual progression of stars at different masses. Maybe that's what I'll do at that time. But I won't spend more time trying to find it now. So awesome. Let me share again. And now the next thing we talked about was, and let me make sure I didn't miss any comments here. So we talked about the minimum amount of mass. I'll come back to Lisa for that 2 weeks from now to exact amount. But we know that the more massive ones will die off the top of my head. I would say over 20 solar masses, but that may be inaccurate. Oh, what's the central temperature of the sun, Catherine says? Oh, at the top of my head is at least 15,000 Kelvin. It's very hot in the center. And as it starts to expand out, it gets cool. So, stellar core. I'll see if I can find that. But the center of a star is extremely hot. Because there's literally nuclear fusion going on. Small. Awesome. Look, I actually found the masses. Oh, no, that's close. I found the radiuses. I guess they're real big on radiuses in this book. Let me shut the book again so y'all can see what I'm seeing. I thought I found the masses, but it's still radiuses and luminosities. So whenever you see a circle like that, that's talking about number in terms of the sun. Because we basically base all of our the way we make things intuitive is to base everything off of something we know, which is the sun. So something is this many solar masses, this many solar radii, and we know what that's like. So let me search temperature stellar core. I have to find that as well. Oh yeah. But the thing about it is we always do Kelvin. Off the top of my head, I would say between 15 and 20,000 Kelvin, because Kelvin is a temperature that's definite. Like basically we normally go off like Fahrenheit and Celsius. I believe that's based off water. Like water freezes at 0 Celsius and stuff like that. But basically 0 Kelvin, if we have something that's at 0 Kelvin, what it basically means it's so cold that the motion inside of molecules and atoms stops. When we get cold, we start to slow down. So the idea is that if something was literally at 0 Kelvin, there would be no movement in an atom. Everything would just stop. So, and then we go up from there from basically absolute zero, and it gives us a very definite temperature to work with. And that's why if you calculate these things with stars and everything, the temperature is always in Kelvin. I suppose you can, well, even, I mean, I'm sure you can convert the equation to work with Celsius, but you have to change the values of everything in order to make it very complicated. Oh, no problem. Lisa, it's my pleasure. That's why I'm here. Some entertainment, some learning, and Brown said it's pretty cool. How can we create these communities of stars based on age and where they are in their life cycle? By literally looking at their color. So, and we're familiar with this, right? Intuitively, like let's say, right, we're uh, at a barbecue, and we know that we have like a piece of coal, and we set it on fire so it's really hot. Um, it could get even white hot, right? And then when it gets really, really cool, it gets red. So we know intuitively that when something is very, very hot, it's on the blue end of the spectrum, and as it gets cool, it gets red. Or if you're looking at a metal, if you're looking at metal like molten metal, if it's sort of cool, it's reddish. But the hotter it gets, it starts to increase its range from the red to the blue, and that's why we say something might be white, white hot. That means it's really, really hot. So when we look at the HR diagram, and I'll pull up another one of those. I'll see if I can find one of the ones that has a good temperature thing at the bottom. All right, so I think this is a good one right here. Let me move my Discord. When we look at an HR diagram, and we can look down here, and we can look at the color of the star at least. So in other words, this OBAFGKM, that lettering, they just randomly pick letters, but that's based upon looking at the frequency of the star, and we know there's something called Wayne's law, where we can look at the frequency of a star in wavelength, and we know that the wavelength will be proportional to its temperature. So all we have to do is look at the frequency of a star, the wavelength of the star. Once we get the wavelength, because wavelength and frequency is interchangeable, so that's why I mentioned the other one. We get the wavelength of the star, we find out the peak of that wavelength, and then we know the temperature of the star. We know that the temperature of the star is going to be related to the pressure and the mass of the star, because the pressure is what's going to be increasing the temperature inside the star, and the temperature is what's going to be driving more fusion. So the hotter a star is, the more fusion is within inside of it, so it'll be hotter. So it all is it's a interactive set of features of stars. So what that means is now when we get the frequency, we know what the mass has to be because we know what the temperature is. We know what mass has to cause the amount of pressure to cause that amount of fusion to cause that temperature. And then we simply put that star on its HR diagram. And we say, okay, this star has this temperature, so it must be this mass. If it has this mass, it must be this radius. Oh, this is a red giant star, so it'll go up here. This star has this temperature. We know it must have this mass, so it's here on the main sequence. So we literally take this data for each star, and we plot these stars individually, and then we get this sequence going on. Now, let's say we study a star system and we find no big stars. We have no stars that's up here in this area. And it's probably better for actually me to show you my drawing of it for this part. So let's say we look at a star cluster and we find no stars up here, right? We find only stars along this main sequence. That means we know we have a very young system because no stars have died yet. If we look at an older system, it'll look like this. We'll see some red giants over here. We'll see no blue stars up there. And maybe we'll notice that the star in the main sequence here has gotten bigger. So let's say the sun has gotten a bit bigger and a bit more orange because it's about to die. And we'll still have these red stars down here because they're so small, the pressure is so weak that they're very dim, they're very cool, so they last longer. So this would be sort of a mid-age cluster. This will be a young cluster because we have a whole bunch of young stars. And again, these stars will still be there, but they'll just be, because they last so long, it's almost like they're unchanging. But what we really look for is the youngest star, the star that's up here on the main sequence that's very hot, so it's burning very fast because it's so hot, because it's so big, has so much gas, so much pressure. So we know if that thing is still alive because it burns so fast because it has so much pressure, this has to be a young system because the young star is still alive. This is a mid-age star cluster. And then when we get to the old cluster, the HR diagram will look like this. We'll have a bunch of these, and it'll just be populated by red giants. And we will have no yellow stars because all of these yellow stars will have died. The blue stars will have died long ago, and it'll look like this, right? And then when we get to something called like a stellar graveyard, you have what's looking like this, right? This is basically a stellar graveyard where uh, all of that gas is from nuclear explosions. It becomes these big gas clouds. So there must have been a very, very immense cluster of stars. So we looked early in the book how they had all those star clusters. You imagine all of those stars die and explode. That gas just expands out. Now you have this field of gas, and eventually gravity starts to pull them back in, and then you see these clusters, these bright clusters, because again, these stars start to build up and make more stars. Now the thing is, by the way, I actually put this image together myself from the Hubble data. I'm not so good at it yet, but this is an image that I put together from the Hubble data, and so I can't really say how accurate the colors are. It just basically, I just roughly took different images and put them together in the RGB. Something I have to do for my homework because we have to actually be able to do this stuff and know how to do it to pass the class. So yeah, but those regions that's pink may actually be blue, but they are star forming regions. But that's why it's mostly surrounded by gas because it's still basically, you could almost say that a stellar nursery is in the midst of a stellar graveyard. So the stellar graveyard is all the gases, which is the nebula from the exploded stars. But then when gravity starts to contract those again, it starts to birth new stars. But the thing is, those big stars that exploded, the high pressure started to fuse heavier elements. So now the new stars have heavier elements. And then when they start to die, they fuse even heavier elements. And now we could live because we have carbon and magnesium, all of these things that were fused in stars originally, iron, lithium, all of these things that were fused in stars that form the foundation of our bodies and everything. And Bronx says it's pretty cool how we can create these communities of stars based on age and where they are in your life cycle. Yes, it is very cool. And we learn a lot about the universe from that. As a matter of fact, I mean, this is how a lot of this data is correlated. Like, for instance, one of the ways that we can age stars is not only by the HR diagram, but um, we can look at a star and put filters on it when I say age and distance. So one thing to keep in mind, by the way, um, age is very correlated with distance in astronomy because the farther we look into the past, the older we're looking. The farther we look in distance, the farther we're looking in the past because the light had to travel so many thousand light years to reach us. So if something is 1,000 light years away, the light took us 1,000 light years to get here. So we're looking at that star cluster, for instance, how it looked 1,000 years ago. Well, another thing we can do is there's something called the hydrogen alpha break, where if, like for instance, looking at that cloud that we see right there, there's a lot of hydrogen there. And if you have neutral hydrogen and you have a star or something behind that cloud, if you think back to the spectra I showed in my debate, that hydrogen will absorb that spectra, and then when we get that light, it'll be missing hydrogen at that wavelength. So what we can do is, when light reaches us, it's redshifted. We can actually look, and maybe it'll help if I drew this. We can actually look and say, okay, we know that hydrogen emits at this wavelength here. We know there must have been a cloud in between the star that we're seeing that absorbed that hydrogen. So this is a big cloud of hydrogen. And so now we have a dip where hydrogen should be, but that dip has been shifted by a certain wavelength because of redshift. The farther away it is, it redshifts. So all we have to do is shift this back to where hydrogen would be, right? So now we know how much hydrogen shifted because of redshifting, and then we can back calculate that to find out how far away that solar system must be, right? And then when we find out how far away that cluster must be, and let's say we look and we find out how old the cluster is, it'll all correlate with how far that must be, how old it was when it was born, and how distant it is away in the universe. It all correlates. So that's how we can correlate all these distances, the ages of stars, every single, we could do it by wavelength, we can do it by temperature. All of these things correlate, and they all give us the same answer. Similar to how I was talking earlier, you could take a Foucault pendulum and it'll give you a spin and it'll match your latitude, and then we can do a whatever type of device that was, and it'll give you the 15 degrees is more accurate. And all of these things match up, so it's pretty cool, right? And Real Cognitive says, and the ranges and sizes of skill is really something. Seeing the new nifty viz, yes. Yeah, I saw those before. You probably talking about like what it does. Real Cognitive is like it goes like this is the sun, like it goes this is the sun, and we see it, and then it like moves the sun down, and then it's like this is Rigel, and we see what Rigel is, right? And then it moves those down, and this is the sun, this is Rigel, and this is like Beetlejuice. Yeah, I've seen these before as well. It's pretty amazing. Uh, uh, and again, that's one of the ways we know, because we can look at Beetlejuice and we can see the color. And maybe y'all might like to see that. Let me find Wayne's Law for y'all, because this will be like the second time I'm mentioning it. So let me pull up Wayne's Law real fast so y'all can see what I'm talking about. Wayne's Law. See if I can find the actual equation. Okay, here we go. So it has the proportionality. It doesn't have the full equation, but this is the proportionality. That's what I was talking about. So the wavelength of peak emission is proportional to the temperature. So, oh, didn't mean to scroll. There we go. So if we look at this diagram here, we can see the pink wavelength of frequency of emission of a star versus the temperature. So if we look at here, this is a 4K star right here, and you see it's peaking almost invisible. And now it's understandable why the sun, right, it peaks invisible, because its temperature is right there, right? And that's why the sun is, we consider it, I mean, technically it's like a green, like the peak is really like in green, somewhere like greenish. It's not technically yellow, but close enough. But if you're in outer space, it looks sort of white, because we do get all the colors, because you can see in that temperature range, all of the colors are within that peak. But, if we actually did like a very close analysis, it should be like in the yellowish greenish range where the actual peak is. That's because we know that how the temperature relates to the peak wavelength. So, you know, oh, here we go. So here it is right here. This is the actual equation right here. Now, there's a whole lot of derivation behind it. But the short is, if you have the peak wavelength, 2.99 millimeters divided by the temperature, that's a relationship. So what that means is, if I see a star, right, and I use my devices to get the wavelength, I have the wavelength, right? And now what I do is I divide that wavelength by 2.99 millimeters. That will then give me the temperature. And it's always pretty consistent. And, we always notice the temperature of a certain star. The star is huge and red, for instance. Or if it's very huge and blue, it's a very young star, but it always matches it with its turn off on the HR diagram. Whatever we're looking at matches. So if it's cool and red, the temperature will be, like, it'll be bright, I meant to say. It'll be very bright, but the temperature peak will be, towards the reddish side. And if it's blue, like Beetlejuice, the temperature will peak towards the blue side, and the size will all match. Everything works out. So it's pretty cool. But that's Wayne's Law right there. So we can use this to get the size and temperature and see how it works. So the sun, well, 5.9 something, but mine was like 5,900 or something like that, whatever it was. But we know that stuff. We can get that stuff pretty easily. Cooler stars, 3,000, and so on and so forth. So it's pretty fun, man. I like it. Find it pretty interesting. Is that rounded up? Pretty sure it's rounded up. Yeah, because the units can get pretty intense. So I'm pretty sure that's rounded, but This was an intro book, so we did calculations, but we didn't have to get pretty precise. It depends on what you're trying to do. Like for instance, mine when I took the spectra, I wasn't pretty precise on my spectra. I got the rough periods of where the elements were, and I was able to see, oh, that's H alpha, and so on and so forth. But I didn't go so far as to get the normalization so I could find out how much each is there. I still don't know how to do that actually. But maybe I'll learn how to do that because I'm starting to get my research more focused so I can find something specific and work with my mentor and I'll see what specific aspect I'll look into. I'm thinking about actually trying to see right now I'm looking in the papers to see if there's a survey of let's say the distribution of rotation of stars in the Milky Way galaxy, for instance. So I found different surveys, but I have to read the papers to see what the breadth of the surveys are. And but if that's not the case, I might try to see if I can do some kind of. The thing is, the data is there. I'm learning in this class now how to access these databases and get the data. Like that's how I was able to get the picture there. So the data is all there. So if I could find out where to get the data on certain stars in a survey, so I can get the rotational data, I may be able to plot similar to an HR diagram, but imagine an HR diagram of rotations, and I could try to see if I can establish a relationship not only between the distribution of rotations in the Milky Way galaxy, but maybe rotation relative to temperature, rotation relative to size. Pretty sure somebody did that already, but I haven't found this specifically yet. But my mentor was telling me it's surprising how you can go into the old data and there's just some questions that people just never thought to ask, you know? So you can actually go to the matter of fact, if you look at Kepler's laws, Kepler's laws were based upon old data, if you think about it, because Brahe is the one who did all the observations, naked eye observations, but it was pretty good. He died, and Kepler came along and looked at that intricate data and thought about it a different way and came up with Kepler's laws, right? So the data, for instance, that made that image there is accurate enough to give us a very accurate representation of what's there. But now the point is, what specific question can I ask about that group of stars, for instance, that I can extract from the data? And the reason why I say from the data because I know I'm not going to be able to get access to like a Hubble telescope myself to be like, I want to look at that. Like, no, you gotta, it costs a lot of money to. Well, now it's all about the JWST actually, but you got to be doing some serious work to like take control of the GST for a little while. But what I can do, I can access the Hubble data and the JWST data, and do the stuff I'm learning in my class, and I'm getting access to all the different databases and all that stuff. And so yeah, I'll probably be showing y'all more images as I go along. And if y'all let me know if y'all have some interesting thing y'all know about that y'all want me to find, I could try to find the data and see if I can put the image together. Let's see if there's any other questions I missed here. And I forgot to do that. I'm glad you mentioned that. I was supposed to show you the range thing. So let me get that calculation, and I'll share all that calculation, and I'll close up. Keep this one about an hour. And the one next week will be on, let me remind myself what that topic was. So next week, I'll do tides and gravity, which is interesting because I know I'm going to have to deal with that in my classical dynamics class. Eventually, I know in the middle of the semester, we're going to have to start calculating the tides and see how that works. So that'll give me a head start on that. So next week, I'll talk about tides and how gravity plays with that. And what I'll do the week after that, so the Saturday after next, I'll do stellar evolution, and I'll have the actual masses for, this mass of a star becomes it's a red dwarf. This mass of the star is like the sun. This mass of the star becomes a supernova. This mass of the star becomes a white dwarf, and I'll talk in more detail about the progression of how that works. But for the time being, let me show you this calculation. It was actually a class activity we did that I got that distance from. And I'll leave you all with that. So here's my pad, and this is the way it works. I was talking about how accurate those images are, right? So in that image I have right there, in that image right there, so this is the data from that image. In that image, every pixel is a certain size. Like every pixel is a certain size across the sky. So every pixel in that image, oh, wrong button. Every pixel in that image is 2.7 times 10 to the negative 5 degrees. That's this right here. Oh, sorry. I took my, here we go. So every pixel in that image is this. It's 2.7 times 10 to the negative 5 degrees, every pixel. So the size of that image was like 2150, something like that. Oh, here it is right here, 2150. So that full image, and right here is just a screenshot, like what you're seeing right there is not the full image. It's a screenshot of the center of it. Like there's a bit more on the sides and above it, right? But the full image is 2150 pixels. So that I was able to multiply that to get the full width of the image. So the full width of the image is 208.98 arc seconds, or about 0.058 degrees. So that entire Eagle Nebula right there, they call it, that entire thing is only about 0.058 degrees in the sky. So you imagine that. I mean, you know how much a degree is. It's like a little, I mean, it's a very sliver of the sky has that entire thing in it, right? So the professor gave us the distance. Oh yeah, all that data is available to anyone. All you got to do is just search for it. Just go online and search JWST, search Hubble. And the reason why is because the data is achieved with taxpayer funds, right? We pay for that stuff. When NASA does it, I believe JWST is between NASA and ESA. So that I believe it's in Japan. I believe it's all of them. But all of these things are government agencies, so we pay for that stuff. Now, the only difference is that the scientists who actually get the data, they do have a sort of between 1 and 3 years where we can access it. Because what happens is, let's say this group, like a university, like in my school, UT, they're building another telescope now. They're building this telescope that's going to do a bunch of weird, cool stuff. Since they put the money in it to get it, what happens is they get, I forget what the official word is, but you can say guaranteed time. Like let's say once the thing is built, they have access to the telescope, let's say 2 months. 2 months they have it. And they could do whatever they want with it. And the data they get from that, they have sole access to it for let's say a year, because they're gonna want to analyze the data. They're gonna want to, write their papers about it, and they want to be the first ones to get it out, because that's how you get famous, right? You discover something first. And they put the money in to build the telescope, so that's how they get first access. But after the original people who, built everything, so maybe, the people at that university get their first time, the people at that everybody who contributed, and they have that data for a year, it then becomes public after that year or whatever. And then after that year, then people start putting in proposals to get access. I mean, so technically even you and I can get access, but I mean, I don't know enough astronomy to post something that's advanced enough where they could be like, yeah, you should use the JWST to look at that, right? But I mean, technically, as long as you can write a proposal and you have a good enough question, and you say, man, this we haven't figured this out yet. If I could point to JWST there, you could put the proposal in. I mean, my understanding is anybody can do it, but it's just not many people are advanced enough in it to be able to write a effective enough proposal. But suffice it to say, now Hubble has been out so long that almost all the Hubble data is out, right? And you can get that there. But the thing about it is, like this image right here, this full image was about 700 megabytes. That's how much data it was. I mean, it's an immense amount of data. Like I'm just learning I'm just at the thumbnail size of access to the data, but it has everything. I mean, it has the temperature, the distance as far as the pixel size. You can get the distance from the wavelength. Yeah, all of that stuff is there. It's amazing. So I don't know how to access all that stuff yet, but that's what I'm in class for, to learn how to do it. But yeah, you can look for. So you may not be able to get a JWST image that was taken today, but you'll be able to get one that was taken like a year ago or something like that. So the professor gave us the distance, so we know the distance was that, and I got the angle from the image, which is that. Oh, sorry, I forgot to show it again. So we know that the distance is this. I got the angle from the telescope. So I'm going to simply utilize simple trigonometry to figure out how big the thing is. So at least the part of the image that I took, that they took, I meant to say, the image that I rendered, uh, that area of the sky is about 0.018 kiloparsecs squared. So that's how many kiloparsecs that is. Parsec, by the way, is something like if something is far away from us, 1 arcsecond of parallax of the Earth around the sun will be 1 parsec away. That may not be totally accurate, but it's something like that. Like 1 parsec away will be 1 arcsecond of angular distance, utilizing the revolution of the Earth around the sun as the angle, right? So that's going to be 0.0018 kiloparsecs. I mean, I'll see if I was correct. That's what I turned in. I didn't look it up. I just calculated and turned it in, and I'll see if I got it right. But awesome, guys. Thank y'all for joining. Awesome. Thanks. And you talking about you looked up the distance, Lisa? The distance to that, or what did you look up exactly? Awesome. The definition, awesome. Good. Well, I'm glad I'm starting to remember at least some things. But like I said, though, next Saturday, I'll do tides and gravity. Hopefully, y'all find it interesting. I'll do my best to make it interesting. And the week after that, I'll do the evolution of stars. I'll have the masses and all of that stuff. And so thank y'all for joining, guys. It's always fun talking to y'all. I'm enjoying talking about actual science instead of dirt. So I'll continue doing that. And I realized that the reason why, like, I look at the chat in that debate, and people are still falling for the nonsense, even though I showed, for instance, how we get gravity from the mass of the Earth. That's the first thing I did. And still, Witzer kept saying over and over, there's no mass involved, and people still believe it. After I showed it I showed it right there. And anybody can get the numbers and plug it in themselves. So the inoculation to that stuff is knowledge. So it motivated me to just spend more time learning science and math so I could just make sure I understand it even better and inoculate ourselves against misunderstanding. And even all of us, if we understood it better, we might be even able to explain it better. But even then, I believe even if I explained it better, they still would just make up something because I don't know what it is. But I'll spend a lot more time just focusing on actual science and learning. It's about belief, right? Just believing whatever is amazing. And of course, they say that we just believe. So, but hopefully y'all enjoyed this, guys. I'll leave y'all with the image of the nebula again, the planetary nebula. Well, I don't know if it's technically a planetary nebula now, but it is the Eagle Nebula M16 from the Hubble data. And thank y'all for showing up, and I'll look for y'all next week. Thanks, Catherine. I'll do my best.